Let us consider an example. We will have a velocity selector, which is a device in which we have both electric field and magnetic field, and they're normally oriented perpendicularly to each other. For this particular velocity selector, the magnetic field will be 0.28 Tesla, and the magnitude of the electric field will be 0.46 megavolts per meter. The question is, what must be the speed of a particle that is going through the velocity selector for that particle to pass through the selector undeflected? So let's see what's really happening inside this velocity selector. Here's our particle. Let's consider a positive particle moving with velocity v to the right, and let's assume that the electric field points downwards. From electricity, we know that the electric force then will be Q times E, and for positive particle, the electric force will be the same direction as the electric field. Now, for the magnetic field, which is perpendicular to the electric field, we'll choose that direction to be into the plane of our screen, and we'll apply the rule for the magnetic force, QV cross B. Using our right-hand rule, we know that that direction for a positive particle moving with a velocity to the right in the presence of magnetic field that points into the plane, the direction for the magnetic force will be up. And here you see why we would use such a device. For some particles, for all the particles that are passing through the velocity selector, the electrical force and the magnetic force are always in the opposite direction. But for select particles with specific velocity, those two vectors will be not only in opposite direction, but equal in magnitude, and they will cancel out. So if we were to place a screen there with an opening in the middle, only particles for which the two forces cancel out overall and experience no net force will be able to actually make it through that opening. And that is where the name of this device comes from, velocity selector. We're selecting only the particles that are moving with velocity v. A little bit larger velocity, a larger magnitude, that means the magnetic force will be stronger in magnitude, and such particles will be deflected upwards towards the direction of the magnetic force. For particles that are moving with velocity with magnitude less than this v, then the electrical force will be stronger and they'll be deflected downwards here on our diagram. So the question in this example is, what is the speed for the particles that actually manage to travel straight along the straight line and manage to go through the opening, for which the net force is 0 according to Newton's laws? Or we can just simply write that the sum of the electrical force and the magnetic force have to add up to 0. When we add vectors, the easiest thing to add vectors is actually by components. So let's just draw an axis. I'll just choose a positive direction upwards and I'll mark my axis to be y. With that choice, the magnetic force and the electric force will have 0 components for the x and the z dimensions, but along the y, they will have non-zero components. For the magnetic force, the components will be 0 plus QVB and 0. And for the electric force, I will have 0 for x component minus QE for the y component and 0 for the z component. So now with that, I can actually write only the equation for the y components. Plus QVB minus QE has to be equal to 0. Moving the QE term to the right and canceling Q, we see that the velocity times the magnetic field must be equal to the electric field. Or for the velocity of the particles that make it along the straight line through the opening, the velocity must be equal to the electric field over the magnetic field. From here on, we just have to plug what is given. Electric field is 0.46 10 to the 6 volts per meter. Magnetic field is 0.28 Tesla, which gives us for the velocity of those particles to be 1.64 10 to the 6 meters per second.